Hello everyone and welcome. Today I'll be sharing a new perspective on database indexing from the paper The Case for Learned Index Structures written by Kraska and his team and presented at SIGMOD in 2018. Instead of using traditional structures like B-trees, this paper shows how machine learning can create indexes that are both faster and smaller by learning patterns in the data. Over the next 20 minutes, I'll cover the motivation, the main challenges, the proposed solution, and what the results show us about this promising approach. Let's begin by understanding the problem the authors are trying to solve. Traditional indexes like B-trees or hash maps are built to handle any kind of data, assuming worst-case scenarios, but real-world data often isn't random. Think of time series data or geographic coordinates. These follow patterns, but standard indexes don't take advantage of that. As a result, they do more work than necessary and use extra memory, storing many internal nodes and pointers. For example, B trees always do log n lookups even if the data is predictable enough for constant time access. So the big question becomes, can we take advantage of the natural structure in data and use it to design smarter indexes? That's where machine learning comes in. The core research question the paper explores is, can machine learning models learn the data distribution and use that knowledge to replace or enhance traditional index structures? If a model knows where keys are likely to appear, it can predict their position directly instead of walking through a tree. This shifts indexing from a pure algorithm to a prediction task, opening up new performance possibilities. But it also produces new challenges. Let's talk about the major challenges that comes with using machine learning for indexing. First is performance. Traditional indexes guarantee fast and reliable lookups. ML models may not. They can be unpredictable. Second is accuracy. Predictions can be wrong, so we still need a way to recover and find the correct result. Third is model size and speed. Deep networks are too heavy for indexing, so models must be small and fast. Fourth, any solution must integrate with existing systems. We can't throw out everything and start over. And finally, keeping models up to date as data changes added even more complexity. Let's move on to the core idea of this research. At the heart of this research is a very simple but powerful idea. Indexing is really just a way to map a key to its position in a sorted list. And that's something a model can learn. If we know the CDF or cumulative distribution function of the data, which tells us the percentage of keys less than or equal to a given key, we can estimate the key's position by multiplying the CDF value by the total number of keys. For example, if key K lies at the 25th percentile, then it's probably about 25% into the sorted array. So instead of walking through a tree, we let the model predict the key's position. That transforms indexing into a prediction task. The diagram on this slide shows how that differs from a B tree. In a B tree, we have to go through multiple levels, but with the learned model, we can jump directly to a position potentially much faster. Now, one model to learn the entire CDF might not be practical. It could be too big, too slow, or just inaccurate for edge cases. So the authors designed a Recursive Model Index or RMI. This is a multi-level model where each level refines the prediction made by the one before it. The top-level model makes a rough prediction like identifying which general region the key is in. Then a second-level model trained specifically on that region gives a more precise estimate. The design is inspired by the mixture of experts concept in machine learning, where different models specialize in different parts of the problem. Each individual model stays small and efficient, and the hierarchy lets them collaborate to make very accurate predictions. The diagram shows how each level narrows in on the correct location, reducing the need for multiple B-tree node lookups. Machine learning models can make mistakes, especially on edge cases. To handle this, the authors proposed a hybrid index design. When the model's prediction is off by too much, the system falls back to the traditional B tree to guarantee correctness. This ensures that we always find the right result even if the model fails. It also allows gradual adoption. You can try the learned index and still rely on proven methods when needed. This hybrid approach balances speed from ML and safety from traditional indexes. Now that we have seen how the system is built, let's walk through how it actually works step by step from data to result. We start with the input data, like keys from a sorted list, log entries, or timestamps. Instead of building a B tree, we first train a model that learns the pattern in the data, usually using the recursive model index or a hybrid with traditional indexes. When a query comes in, the model is used to predict where in the data the key should be. Because the prediction might not be perfect, we do a narrow search around the predicted spot, much faster than scanning the entire data set. If we find the correct value within that range, great. We return the result directly. But if the prediction is way off, we then fall back to the traditional B tree to make sure we still get the right result. This whole flow keeps things efficient while still being safe, combining the speed of ML and the reliability of classic indexes. Even with the good prediction from the model, we usually don't land exactly on the right key. That's why the system still needs to search nearby to find the exact value. But instead of doing a full binary search, the authors propose smarter search strategies. They use biased binary or quaternary search. And importantly, these searches start close to the predicted location, not at the beginning of the list. The model also tracks minimum and maximum error bounds. These bounds define a small window around the predicted position, so the system only searches in that limited area. That makes the process much faster than a full range search. They also mention enforcing monotonicity, which means making sure predictions go up as keys go up. This helps the search remain stable and avoids unexpected behaviors. These small improvements really help make learned indexes practical for real world use. Let's move on to how they tested it. To test their approach, the authors evaluated learned indexes on several types of data sets. A weblog dataset with 200 million timestamps, a maps dataset with longitudes, and synthetic log-normal data to simulate skew. They compared the learned index to optimized in-memory B trees, focusing on lookup time, memory size, and training cost. This setup gives a solid view of how the models perform in different situations. Integer datasets. On integer datasets, the learned index showed major improvements. 3 times faster lookups, up to 100 times smaller memory footprint. Even simple two-stage models outperformed finely turned B trees. This is largely due to skipping tree traversal and using compact model parameters instead of large node structures. This table compared the performance of B-tree and learned index structures across three datasets: map, web, log normal, using different configurations. Metrics include index size, lookup latency, and model latency, with lower values highlighted in green and better performance ratios in parentheses. Overall, learned indexes consistently use less memory and achieve faster or comparable lookup times, especially with larger second stage models demonstrating significant improvements over traditional B trees. String indexing. Indexing strings is tougher because of variable length and tokenization overhead. In this case, the dataset had 10 million document IDs. While the learn index didn't achieve the same gains as these integers, the hybrid model kept performance competitive. They also used bias container research to help with accuracy. So it still worked, just with more limitations. This table compares traditional B trees with various learned and hybrid index structures based on index size, lookup latency, and model latency. While learned, the hybrid indexes significantly reduce memory usage. They can have higher or comparable lookup times, with learned QS achieving the best trade-off between size and performance. Hash maps. The learn indexing approach also extended to hash maps where we typically hash keys into bucket. Here the model predicts the position directly based on the data distribution, which reduces collision by 77%. That leads to faster lookups and better memory efficiency. Since the model is compact, it's also more lightweight than larger hash tables with many buckets. So this shows that learned indexing works beyond just sorted arrays. Bloom filters. Bloom filters are used to check if the key might be in a set, but they allow false positives, not false negatives. In this case, a binary classifier predicts if a key exists, but since ML can make mistakes, they use an overflow Bloom filter to catch false negatives. This hybrid setup maintains accuracy and reduces memory usage by up to 36%. Again, this highlights how learned models can improve even specialized structures. In here, line graph compares the memory footprint of traditional Bloom filters and learned Bloom filters in different false positive rates. Learned Bloom filters, indicating in blue-green lines, require less memory than traditional Bloom filters, indicating in red line, for the same false positive rate. When we consider the Bloom filter architectures, A shows traditional Bloom filter insertion using multiple hash functions to set bits in a bit array. B shows learned Bloom filter insertion where a model predicts the position in the bit array. C frames Bloom filters as a classification task where a model predicts set membership, falling back to a Bloom filter for uncertain cases. Learn indexes offer several powerful benefits over traditional structures like B trees. First, they provide much faster lookups, in some cases up to 3 times faster. That's because they can predict the position of key directly rather than traversing a tree. Second, they are extremely space efficient. By modeling the data, they can reduce index size by 10 to 100 times, which is especially valuable in memory constrained environments like mobile or edge devices. Third, learned indexes can adapt to the data distribution. They learn patterns in the data, for example, clustering or skew, and use that to make smarter predictions. Finally, their hybrid support makes them practical. If a prediction isn't accurate, the system can fall back to a B tree, ensuring reliable performance even in worst case scenarios. Together, these advantages make learned indexes a promising direction for optimizing database performance. Despite the progress, there are challenges to solve. First, frequent updates make retraining expensive, so we need models that adapt to changing data. Second, eliminating fallback is still an open goal. Current systems rely on B trees for guaranteed correctness. Lastly, choosing and training the right model takes time. Automating that with tools like AutoML would improve usability. Solving this could make learned indexes even more robust and mainstream. Real world implications. Learned indexes are great for data that follows patterns. Think map applications, where coordinates are clustered, or IoT logs, which are time ordered. They also help in search engines, where document IDs are huge and performance matters. Mobile and edge devices benefit from the smaller memory footprint. And in the cloud, less memory means lower cost and better scalability. So, this isn't just theory, it's practical and deployable. To summarize this paper, reimagines indexing as a machine learning problem. Instead of static algorithms, we use models that learn from data to predict positions. Recursive model indexes offer fast, small, and accurate alternatives to B trees. And with hybrid fallback and smart search, the approach is both practical and scalable. This idea could reshape not just indexing but many core database operations. Let's move on to the future directions. Looking ahead, there are exciting possibilities. Multidimensional learned indexes for spatial or multimedia data. Dynamic model updates for real-time systems. Hardware acceleration using GPUs or TPUs. And applying ML to joins, sorting, or caching, not just indexes. This research is a starting point for a large shift toward intelligent ML driven database systems. That brings us to the end of this presentation. Thank you very much for watching and taking the time to explore this topic with me. I hope this has given you a clearer understanding of how machine learning techniques can enhance modern database systems and why this area is attracting so much interest in both research and industry. I'd be happy to take any questions or discuss your thoughts on the role of machine learning in database systems. Once again, thank you for your time and I hope you found this session helpful and informative.